Just say sorry, Nixon. He is listening. He's always,
I didn't hear
he's
him.
always listening. I can always tell when people are interrupting the conversation.
John, you're the presenter today. Do you still have the derivatives from 20 and stuff on your calculator?
Yeah, probably.
Okay, good.
I can barely see the words in the
Go to there, and we're going to talk about that here in a second. All right. Now, tomorrow. Well, hi, Richard.
Oh my
Sydney was enjoying her foot.
Yeah.
All right. Now, I'm recording today, but tomorrow I'm going to record second block.
Where are you going?
Because you are then going to watch it third block.
Oh.
So, how exciting that will be. So, Mrs.
So it's kind of a concept. The videos usually take once 40 minutes long.
Mrs. Smolik will be here. Actually, I will be here. I will be here at the beginning to get started. So if you need her to pause it, or well, let's see. That means I'm gonna have to leave my computer here. Okay, well, I can't do that.
You get it.
Yeah.
Perfect. It will. I'll have it up. I'll have it up.
on YouTube and we can get the password for it.
Bring your computer. Thank you.
Or I might be able to try and get around it. I've been able to do that 2 times.
I think we can wire it. We can use an Ethernet connection, so we should be fine.
Okay.
That should work, right?
Cool.
Yeah.
You
There's
could
no
also,
password.
if you have it saved on your thing, you just leave it in a USB on the SD.
Yeah, and we can plug it into my computer USB too.
Oh yeah, that'd be easy.
So if
That'd be
you
easy.
put it on a USB and
I'll just save the file on
a USB.
USB. Okay. Good plan. Thank you. So, but I'll be here at the beginning so we can get that all hooked up and going. And I think, yeah, it'll be very exciting, but it'll be good. It'll be necessary, I think, as you see, to get the stuff. There'll be some homework. So, anyway, let's get into it. I want to spend just a quick amount of time on parametrics, but then we're going to get into the new thing today. Now, on parametrics, on our next quiz, you'll have to be able to do these 3 things. The next quiz is a lot of story problems. The other sections we have to do yet are all of that, story problems. But parametrics, like the baseball problem, that kind of thing, something maybe similar to that, but mostly for parametrics, I want you to be able to graph a parametric equation like the early problems were here, mark the direction of travel, be able to trace, understand that x prime and y prime are horizontal and vertical velocity, right? So if I just give you a parametric equation and say, what's the horizontal velocity at this point, that you understand that means x prime, okay? What's the speed of the particle? Know that formula, okay? What's the slope of the path? Know that, y prime over x prime, that kind of stuff. And so a lot of it will be fairly simple from that standpoint, as far as just knowing those things that's on that page. Yes? I think this quiz will actually be all calculus. So being able to graph it on the calculator, trace, and so forth, being able to work out those formulas and so forth. Now, I do want to talk a little bit about 20. I want to talk a little bit about 14, and then we're going to move on.
Do you know when approximately?
Yeah, probably about next Friday is what it's looking like. Okay. So let's. I'm hoping to get to that point, so we don't have to do a Monday one again. But so let's talk about 14 just a little bit. 14 said x is equal to 2t, and it said y was equal to, what was it, 3t plus 4. And so you have in part A you were supposed to graph it, okay? But all right, so fine. Be able to go into your parametric equation, be able to graph it, you need to be able to do that. Essentially what you got then was you got a line segment. All right, both of the x and y equations are linear, so it's not a surprise that it was linear. So you had a lot of work on today's homework with these linear equations. But I got the sense in talking to people that people didn't quite understand, still are not quite understanding this whole thing about parametrics, that x is its horizontal position and y is its vertical position, so at a certain time. So when they said, where is the particle? What's its location at t equals 0? You just plug a 0 in for t, and that gives you x is 0. And then plug a 0 in for t into this equation, which gives you 4. What that's giving you is a coordinate of where the particle is at time 0. So that would be 1, 2, 3, 4. So that would be the point 0, 4. And then they said, where's the particle t equals 1? So this thing went from 0 to 1. So just for 1 second, imagine. And you put a 1 in here, and you get 2. And you put a 1 in here, 3 plus 4 is 7. And so the particle was at 1, 2, 1, 2, 3, 4, 5, 6, 7. Okay, and this was the little graph you would have had, this line segment. Then they wanted you to write it, the part B, they wanted you to write it in terms of just y and x. Well, that's where we did this solving thing. So take this first equation, divide by 2. So you get 1/2 x equals t. Then take that and plug it back into there. So we get y equals 3 times 1/2 x, would be 3/2 x, plus 4. So what you realize is, oh yeah, that line is just that equation right there. 3/2 x plus 4. It has a y-intercept of 4, have a slope of 3/2, and so forth, right? That makes sense. Then the part C said, what's the slope of it? Well, we just got in saying we could tell it's 3/2, but what was our parametric formula for slope? Y prime over x prime. Well, what's y prime in this problem? What's y prime? You look here, it's 3. What's x prime? 2. 3 over 2, sure enough, 3/2. Then they said, well, why doesn't it depend on t? Well, why doesn't it depend on t? Why is the slope always 3/2? Well, no, because on some it does depend on t. Only on this one it doesn't depend on t. And I think somebody said it because it's what? It's linear. Since it's a line, the slope is going to be 3/2 at any time because the particle is moving on a line. So the path is a straight path. And so therefore its slope is always 3/2. But if you had the Adam ant problem, right, at a certain time the ant's there, it's got that slope. At another time it's this slope. At another time it's over here, it's got this slope, right? So those would depend on t. Now, we haven't done a problem that had that. I mean, so what was the Adam ant? I could give you a problem that asks for a slope equation for the path. Well, what you would do is you take the y prime, and on Adam ant, I think y prime was like 0.4 cosine t. I might mess this up, but it was something like this. Minus 0.4 t sine t. I think that was the y equation. I might have x and y mixed up. Doesn't matter. You'll get the point. And the x prime is like 0.3 plus 4 cosine 2t or something like that. That would be the slope formula for Adam ant. This would tell us, it's a pretty messy looking thing, but we have calculators, so that could handle no problem. What this would be is the slope of Adam ant's path at any time when he's on that path. Okay? It's the y prime equation over the x prime equation. Now what we did on the worksheet is you plug the 6 in, I think, right? You plug the 6 into y prime, a 6 into x prime, got those numbers, and then divided. But we could literally just divide the equations and have one big equation for the slope. And the same thing with speed. On the baseball problem, I think one of your questions there asked you for, I think it was 17C. It asked you for the speed equation. Well, on 17C, the speed equation would simply be x prime, which was 150 squared, plus y prime, which was negative 32t squared. That would be the speed equation for that baseball. It's x prime squared plus y prime squared. And then if you want to know the speed at any time, you just plug in t. Okay? So that's the speed equation. So we can find speed at certain times or slope at certain times, or you just have a slope equation and a speed equation at any time, using, again, x and y. All right. So that was what I wanted to talk about on 14. And then on 20, and we'll go to John's calculator here. On 20, what we said was, arrow back up a little bit. On 20, they gave us a new equation for x instead of the 150t. Keep going. You have more? Keep going. Keep going. There you go. Right there. Okay? This was the x equation that they gave you in number 20. Right? With air drag, with air resistance. Okay? And then, of course, we have the same y equation. It was a 16 minus, or 7 minus 16t squared. So it's very much the same baseball problem. Now, the first question they asked was, what was the first question on 20? Where does it, at what time does it cross the plate? Do you have that? You probably have that up farther. Keep going. You're almost there. Right there. Okay, at what time does it cross the plate? Well, what do you know when it crosses the plate? 60.5 feet away, right? So he throws it from here, and when it crosses the plate, that's 60.5 feet later. That's what variable? The 60.5 is the, no, that's the horizontal distance, right? What variable is horizontal distance? X, right? X is horizontal position, Y is vertical position, right? X horizontal position, Y is vertical position. Again, it comes back to the basics of parametric equations. X is horizontal distance, Y is vertical distance. So when it crosses a plate, its X coordinate is 60.5. So what he's done is he's put 60.5 in for X. Right? Now, this is really supposed to be what right here? This is the T, right? So we don't confuse those, right? I mean, he used X, and that's fine on the calculator. This is the T, and this over here is the X, 60.5. So he took that equation that they gave you in the problem on number 20, he set it equal to 60.5, and he solved it 0.442, right? So that's when the ball crossed the plate, 0.442 seconds. Then they say, how does that compare to the one we did yesterday, right? The one without air resistance. And that was like 0.403 or something, right? 0.403. So it took a little longer. It took a little longer to get there because the air resistance slowed the ball down. Okay, what was part B? And what height does it cross the plate? What variable is that? The height. That's y, right? So what did he do here? He did something kind of goofy. Okay, finally right here. This is probably better. What is all this? Did that work? Doesn't look like it.
Yeah, I just put the exact.
You were trying to, the problem is it had that x equals. You know, I mean, what you do is you went up and grabbed that because you didn't want to use the rounded value, which is important. The rounded value. By the way, I figured out why we were getting the wrong thing this morning on that rounded value. Were you getting one that was getting?
Because we didn't square.
We didn't square the whole thing. So, but right here, you wanted to grab this whole value, but the x equals was causing the problem. So you'd have to delete off that x equals. Okay. So he came in here. So anyway, 3.87. Notice how it's a little. If he doesn't. If you just use 0.442, look what he's got, 3.874, when it should be 3. Actually, that did kind of work, didn't it? It did work. He just gave it weird. Yeah, I guess it did work, but it just looks weird. 3.871 is what it should be. Remember, you got to be accurate to 3 decimal places. Okay, so he's just taken the 0.442 for t, and he's putting that into the y equation. Okay, putting that into the y equation, and so you're getting that. So that's how high it was, so 3.871 approximately, so that would be a strike, probably 3.5 feet or whatever, that would probably be good. Okay, scroll down then, part C. Part C is at what speed does it cross a plate? So now we need x prime and y prime. Okay, so now keep going down, and right here, okay, so here's where he did x prime, right? And again, on the quiz, it's going to be all calculated. So you get a messy looking equation like this, and trust me, you're going to see some of those today. We're going to get some messy looking functions, equation we're dealing with. You can use your calculator to do those derivatives and stuff. So he just put in the derivative. Now he did with respect to x. We could have done t, right? But that's the x equation. He did the derivative of. Okay, and it gave him that. All right, and then what's he wanting to do? He's wanting to square that because he's going to do the speed, right? So he's going to do the speed, and notice he's putting in the 0.442. Now I think did you put in more numbers or no?
Yeah.
Maybe. So here's his, well, we'll just go with this. Okay, so here's his speed equation. the x prime, excuse me, here's the x prime, and he's put a 0.442 in for x, and then here's the y prime, it was negative 32t, except I don't think he's, yeah, he didn't square that. So I think he did that down here later. There it is. There it is. So there was his x prime squared, there's his y prime squared, and then he added those, and then he did the square root of those, and it comes out to be 125.901 or something like that for the speed. Okay, so x, but you can let the calculator, use the calculator to do that derivative for you. And then it says, where does the ball land? Did you do that on here too? Where does the ball land? Okay, stop right there. What happens when the ball lands? The y is 0, right? So he took his y equation, which is this one right here, and set it equal to 0. Okay, so took the y equation, set equal to 0, and the negative, it was root 7 over 4, I think was the value. And then he plugged that back into, they didn't want to know when it landed, they want to know where it landed. So that's the x value, right? So he put, scroll back up, John. So he put the 0 into, one more. Okay, so he set the y equation equal to 0 to find the time that it was on the ground when y is 0. Once he found that time, then he put that into his x equation right here, except he messed that one up. Scroll down one. This one. He put that time into his x equation to get the horizontal distance of where it was when it landed, which was 86.85. Okay? The secret to this, and actually the secret to all of these story problems that we do, is when you have these equations, because you're going to work with multiple equations, you've got to know what they represent. You've got to be thinking about what the equations represent. You've got to understand that x is a horizontal distance, y is the vertical distance. X prime is a horizontal velocity, y prime is a vertical velocity. The speed equation, what it represents. The slope of the path, what it represents. Okay? And then some other equations we get into today. Indeed, the problems we're doing today. All right, so that is pretty much it for parametrics. We'll come back and revisit this a little bit as we get closer to the quiz, but those are the things we want to be able to do. All right, so go ahead and get your notes out, and you might open up your books or turn your books to, I'd say page 234 would be a good page to be on. 234. All right, so we're going to talk about section 4.3. Now, remember what I said about chapter 4. Go ahead. Each of these sections is kind of discrete and distinct and unrelated to the other sections, except for the fact that it involves a derivative somehow. All right? And so what we just did in parametrics is, pretty much separate from what we're doing in section 4.3, other than the fact that derivatives are involved. So 4.3 is about something called optimization. Optimization. So when you hear the word optimization, finding an optimum outcome means what? The best outcome. And so if I was running a business and I was selling some product and I was interested in making profit, the optimum outcome would be the biggest profit, the maximum profit, right? If I was stranded in the snow and wanted to get to a gas station to get warm or make a phone call or whatever, then the optimum time it would take me to get there would be the least, right? So the minimum time would be the optimum in that situation, okay? And so depending on the situation, the optimum might be a max or it might be a min, Now, I suppose you could argue that maybe there's something in between, I don't know, but when we talk about optimization, we're talking about max or min, okay? Now, we've already done this in a mathematical sense, but we haven't really done it in real-world application kind of sense, and that's what we're doing today, okay? That's what we're going to do for the next couple of days. So I want to go back and review what we learned back in Chapter 2, okay? Because these are global max-min problems, not local max-min, global max-min, all right? So when we learned about global max-min, remember list of candidates, right? What were the candidates? Where did you look for max and min? Endpoints, where the derivative is 0, and the one we didn't talk about back then, well, we did a little bit, derivative undefined, okay? And I want you to think about this a minute. If I have a function, and I'm interested in its highest or lowest output, because that's really what we're talking about. When we talk about max or min of a function, we're talking about its biggest output or its littlest output, right? Y value. There are a lot of different things that could happen. For example, you could have that. Well, there's the lowest output right there. What's true there? The derivative is undefined. Okay, now if it was like this, the derivative is 0. But you could have a problem like this. Where's the minimum? At an endpoint, right? The maximum is at the other endpoint. Now this graph wouldn't have any max, because it just goes on forever, right? So it's possible you get a function that doesn't have a max or doesn't have a min. If you had a parabola that did this, it would have a minimum or a maximum, but it wouldn't have a minimum because it keeps going, right? Most of the problems we deal with are going to be on a closed interval. So we will have endpoints. At the bottom of page 234, it says if f is continuous on a closed interval, continuous means no gaps or breaks or weird things happen. If f is continuous on a closed interval, then there will be both a max and a min value. And if you go up to the top of page 235, it says a continuous function on a closed interval will assume its max and min values only at critical points or endpoints. So so I want you to keep in mind then, as we do these problems, that there are 3 places we have to look for our max and our min. Because critical points is 2. F prime is 0, or F prime is undefined, and then endpoints. So when I talk about there being 3 places where a max or min can be, it's at those 3 places. When the derivative is 0, the derivative is undefined, or at the endpoint. And you've got to account for all 3 of those in every problem. So we'll talk about the different ways you can account for them. Okay, list of candidates is a big part of that. But there are some exceptions and so forth. All right. So, let's do this problem right here. Okay, this is one actually from our homework back in chapter 2. Find the max, absolute max and min of this function on this interval. So you'd be given all that information. So what do we do first? Do the derivative. Because 2 of the 3 places we have to look are when the derivative is 0 or undefined. So we do the derivative and we get okay, then what? Set it equal to 0. Now, you will be allowed in your homework and on this quiz to use your calculator. So you could solve. Matter of fact, you could have used your calculator to do that derivative. So, and you can do it to solve this. Now keep in mind on the midterm, on the packets, there'll be some of these kind of things on the no calculator part too, so we've got to be able to do that as well. But on this next quiz, you'll get your calculator. So anyway, what would we do? Let's say there's no calculator. Factor out at 2x squared, leave you with 3 minus 2x. So that'd be either with x is 0 or is it 2/3 or 3 halves? I think it would be 3 halves. 3 halves. But again, use your calculator, that's fine. You know. But it's 3 halves. So 0 and 3 halves. All right, so those are 2 possibilities where the max could be. But now remember, when I talk about the max, I'm talking about the max output of f. right? I'm talking about the max output of F. All right, now, the new thing, remember, we said where F prime is 0, where F prime is undefined, and endpoints. We got to check all of them. So there's F prime 0. What about F prime undefined? We actually need to write this down. F prime, here's F prime right there, it's just cubic. Is F prime ever undefined? When would something be undefined? Divide by 0 is a big one, right? Divide by 0 is a big one. Square root of a negative is another possible one, right? I mean, that's undefined, although that's usually not in the domain of the problem anyway. If you have square root of a negative, it usually was negative in the original problem, that's not in the domain, so not an issue. Usually. The big one is 0 in the bottom, okay? Polynomials are always defined. Remember, undefined means you plug something in, you can't get an answer out. Well, anything you plug into a polynomial, you get an answer. So what you put here, F prime undefined, never. Never good grammar. So, but we have to account for that. There are three things we got to account for here in our search for max and min. Derivative of 0, derivative undefined, or the endpoints. Okay, so how do I now figure out where the max and min is? I got my endpoints right here. No, not a number line. That was local max and min. List of candidates, which means put them back into the original function, right? Because remember what we're trying to accomplish. We want to know when this function has its biggest and littlest y value. So we got to plug back into the original, our candidates into the original function. So I need f of -1, I need f of 2, I need f of 0, and I need f of 1.5. Now we can use our calculator for this. Might be helpful to, because some of these functions are going to be ugly that we're going to work with. And so you're going to want to use your calculator, I think. Okay? So now, are these all in between our endpoints? Yeah, that's another thing you got to make sure. You might get stationary points that aren't in between your endpoints. You throw those out. But these are all okay. So go to your calculator now, John, and let's put in, let's just put in the function. So what was it? It was 1. Wait, let's do this. Just type in the function for me. Now, this is not a solve, okay? We're not solving anything here. We're plugging numbers in. So what was the function? 1 plus 2x cubed minus x to the 4th. So what you do when you're plugging into these things is you just literally write the equation, no solve, nothing else, and then what? I showed you guys this before. Vertical bar. Vertical bar is width. Now, you wouldn't need it on this one, but on some of the ugly ones, it really is helpful. So you do the vertical bar, and then you do x equals, and what was the first one we wanted? -1? -1. I did show you the curly bracket. We did figure out the curly bracket where you could do all 4 of them at once. If you want to do that, that's fine. Okay, let's just do it one at a time. So we get -1, and that's -2. Okay, and now just go up and grab that and delete the -1 and put in a 2 this time. What do you get when you put in a 2? 1, okay, keep going. Put in a 0. That's 1. Okay. What about 1.5? $2.688. 2.6875. Remember, you can give more than 3 decimal places, but you have to give 3. All right? So what's my max? This one. And my min is this one. So here we had a situation where the max was at one of the critical points. The max was in between the interval, but the minimum was at the left edge, the left end. Okay? And so that would be the end of that problem. Your list of candidates is your justification that you checked all 3 possibilities of where the max or min could be. And the fact that you wrote over there that f prime is never undefined tells me that you did consider that. Okay? You have to communicate that. Even though we're using the calculator, listen, you would need all this work on the problem except maybe for this line right here. You know, you wouldn't really need this line if you were using your calculator or this work I did here. you would have this equation and then that answer, but everything else would need to be in a maximum problem. All right, so this is, but we did this in chapter 2. Okay, we did this problem in chapter 2. So let's go on to a problem like what we're going to be confronted with in this chapter. Okay, so here we got a piece of paper, 8.5 by 11. And I think you might remember, I think in this class we talked about this. I showed you on the thing. And we're going to cut out the corners and we're going to fold it up and we're going to make a box. We want to know what size square to cut out to make the largest box we can. Okay? Now, in a minute here, we're going to write down kind of the steps that we follow in one of these problems. But in the last problem here, we were finding the maximum of this function f. What is it we're finding the maximum of in this problem? We want the max volume of a box. Well, we need an equation for volume in order to maximize it, because then we're going to need to do its derivative. What's the volume of a box? Length times width times height. Okay? You need to identify the thing you're trying to maximize or minimize. For us, it's volume. Okay? See, this is all you'd be given. You'd be given a piece of paper, 8.5 by 11. You're going to cut 4 squares out of the corners of equal size and make a box. What's the largest volume? That's the question. So, step 1, identify what you're trying to maximize. We're trying to maximize volume. Write an equation for it. Length times width times height. Now, it's not going to be very fun to do a derivative with 3 different variables in there. So, we better set up some stuff like this. Like, for example, how big is the corner going to be? Well, let's call that x. Okay? So now, what's the length of my box? That would be this right here, right? Wouldn't this be the bottom of the box? Right in here, and then I would fold up those edges. So what would be this length right here? That'd be 11 minus 2x. So my length over here would be 11 minus 2x. What would be this width right here? 8.5 minus 2x. What would be the height of my box? When you fold up those corners, the height of the box would just be x. Okay? Now, again, here's where the calculators come in. We are not going to be required to FOIL that out and do all that stuff. Okay? This is the equation that we are trying to maximize. We want to find max volume. You're going to hear me say this over and over again. You're going to say, I don't know what do I set up? What equation I set up? I'll say, what are you trying to maximize? I'm trying to find the max volume. Then you need a volume equation. If you're going to try to find the minimum time to walk in the snow and the road to get to the gas station, you need a time equation. If you're going to try to maximize profit, you need a profit equation. Okay? So you identify what it is you're maximizing and you write that equation. All right, so that's what we're trying to maximize. So we're trying to find the max and min of that function v. So what do? I do the derivative. I need to check where v prime is 0. I need to check where v prime is undefined. And I need to check the endpoints. Now, there aren't any endpoints. We'll talk about those in a minute. Okay? On the last problem, the purely math problem, the endpoints were just given to you. Not so in a real-life situation. You've got to think about what they are. Okay, so we're going to go to the calculator. So, John, you're already going? He's already got it. Okay? All right? We go to the derivative. You're going to have to be able to use your calculator to do a derivative. Where'd you go for that, John? Show everybody again. By the 9 right there. Okay? Your derivative key. Okay? Escape out of there, that's fine. But with respect to x, and he typed that in, make sure you put times signs in between. It's probably a good idea, especially outside the parentheses. So he went in and had the calculator do that derivative for him. All right? And then you want to write that on your paper. You've got to write that down. Okay, what you had. So what was that? 12x squared and then we're going to set that equal to 0. Now, is that ever undefined? It's just an x squared, right? It's just a polynomial, so that's no, so I'll go ahead and write that down there. B prime never undefined. Many times it is not undefined, okay? But I need to consider it. Because just when you don't consider it, it's going to need to be considered, right? It's going to have critical points. It's going to have a place where the derivative is undefined. So we got to be careful. All right, so we go ahead and now we solve this. So we just get back on the calculator. So let's go ahead and solve it. Oops, what's he missing? Equals 0. Then do the equation equals 0. Comma x. Okay, so what did we find? We found x is 1.585, or what was the other one? 4.915. Okay, so that, now again, what was x? Hopefully if we've drawn a nice picture, we got things labeled nicely, we look, oh yeah, x was the size of the corner, right? That's what I was looking for. But I haven't shown what's a minimum yet, right? I haven't verified something's a minimum or whatever. And what haven't I considered yet? I got the derivative 0, I got the derivative undefined. I haven't talked about endpoint. Now, this is one that's going to baffle some of you for a while, for a few days, okay? This idea of endpoints. Try to make this as clear as I can. What are endpoints? Let's go back to this problem right here. Well, this one did. In this problem, -1 and 2 are what kind of values? Are those input or output values? Those are input values, right? Endpoints are always input values, right? When we talk about the endpoints are -1 and 2, we're talking about x values, right? We're talking about input values. So what endpoints are your littlest input and your biggest input that you have in that problem, right? I don't even like to use the term max and min because then that confuses with the max min. The max min we're finding are outputs, right? We're trying to find the max and min output in this problem. So I don't like to use the word max and min, but endpoints are your littlest and biggest inputs that you can have in the problem. So let's come back to our problem here. So you have to think your way through it in the problem. In this problem, our input is x, which is these little corners. What's the littlest x could be in this problem? 0. Then you wouldn't be cutting out any corners, right? So you might argue that, well, that's not, then you're not really doing it. But so you could write a sentence that says, well, the littlest x could be a 0, but if that bothers you because you wouldn't have a box in, you could get into limit talk. You could say, well, as x approaches 0, the volume would be what? Wouldn't it also be approaching 0? Because if you don't have a box, you don't have any volume. You just have a piece of paper laying there, right? If you don't cut out any corners, then there's not going to be any volume. And that's clearly not going to be a maximum, right? So you could say that in a sentence. But it is okay to consider that an endpoint as well. So we could do 0. And we could have done this at the beginning, too. But I think this is a good time to think about it because now we're getting ready for our list of candidates. So the littlest x could be would be 0. What's the biggest x could be? 4 1/4, 4.25, right? Because of this side that's 8 1/2. If I cut out 4 1/4 in these two corners, that would use up the whole short side. It's 8 1/2. So I couldn't have x be any bigger than 4 1/4. So my endpoints are 0 and 4.25. What's that tell you about down here? I can ignore that one, right? Because that's outside of my, if I had 4.9, that I couldn't cut a corner that was 4.9 because it's not big. So I can throw out that. Okay? So now what's next? List of candidates, right? I've got my endpoints. I've got derivative undefined. I got derivative 0. So I'm ready for a list of candidates. So I've got V of 1.585. I've got V of 0. I've got V of 4.25. But we already know these two are going to be 0, right? I mean, you can try them. I mean, go back. We'll do it. Let's go back on calculator. Okay? So let's grab your V equation, which is right why we can't really grab the whole thing. I suppose it's probably faster just to type it again. Okay? If we're gonna put this in, let's do that vertical bar thing. I think on our list of candidates, I think that's easy. No. That's V prime. Yep. We want that original equation. 11 minus 2x. 8.5 minus 2x times x, and then vertical bar, and we want to put x equals 0. Oops. Yeah, okay, no, you're good. Okay, sure enough, no volume. Okay, now let's grab it. Let's do 4.25, and that shouldn't be a volume either, because if we use up the whole side of the paper, we're going to fold up, and we won't have anything. We'll have no width, so that'd be 0. And what was the other one? 1.585. Probably should use a few more decimal places, but that for right now, that's fine. Okay, 66. So that's clearly our max. So 66.148. I'll just use that. So 66.148. All right. Now the last step, if this was just a purely math problem, that'd be our max, 0 would be our min, right? We'd go away. We'd be done. But now, in a story problem, you got to answer the question. So what was the question? Well, if the question was, what is the max volume? 66.148 centimeters cubed. Might have been, what's the dimensions of the box? What would you do then? Yes, Riley, what were you going to say? Well, you wouldn't even have to do that. I mean, the dimensions would be, yeah, that would just give you the 1.585 back again. You see what I'm saying? We know x is 1.585, but the dimensions are the length, the width, and the height, right? So the height would be the 1.585, the width would be whatever you get when you put 1.585 into here, and the length would be whatever you get when you put 1.585 into here, right? So there'd be your length, there's your width, there's your height, and then you give the dimensions. Okay, so you just answer the question that's asked with appropriate units and all that. All right? So that is the process. So if you go through there, I mean, that process is very much the same as what we did with the other equation. What's going to be hard about these is the same thing that was hard about Algebra 2 story problems, is getting them set up. Right? Once you guys got to here, once we had this, then that was easy. That is just like Chapter 2. You have this equation, now you do the derivative, set equals 0, the calculator does all for you. That's fine. The part you're really going to have to work hard on is this part, getting the problem set up. Okay? And that's the part that we will be working on over the next couple of days. All right, so in your notes, and we're going to do another one here, and then we'll give you some work time. Okay, in your notes, I'm going to give you here a kind of a recipe, a little bit of steps in these problems. I'm not a big fan of doing this because what you really need to do is understand the process, understand what it is you're trying to accomplish, and what each step gets you along the way. And so you shouldn't need these set of steps. And I hope you use them maybe in the beginning as kind of a crutch a little bit, but then it's not like you have to memorize them necessarily. All right. So the first thing is identify the quantity that's to be maximized or minimum. The last problem is volume. So we identified that we were looking for max volume. Maybe we're looking for minimum time. Maybe we're looking for max profit. Whatever the problem might be about. Okay, step 2 is write and label, or potentially label, an equation of that quantity. So the next step is to write a volume equation. So again, I will be able to say, well, how do I set this up? I'll say, what are you trying to maximize? And you'll say area, trying to find a maximum area. then write an area equation. You need an area equation. Trying to maximize volume, write a volume equation. That's called the primary equation, or some books call it the objective function. Write down the thing, and it's going to have a name. V equals, D equals, P equals. It's area A equals, right? You're going to, f of x equals, right? It's going to be, have something. Then you're going to do the derivative of that here eventually. Now, often that will have more than one variable. Ours had length times width times height. If you're doing the area of a triangle, it would be 1/2 base times height. Right? That has more than one variable in it. So, the next step, get the equation in terms of a single variable using other information in the problem. And that other information is called your constraints, or your secondary equations, or whatever. In our case, it was when we drew the picture and we saw the x, we could tell the length was 11 minus 2x, we could tell the width was 8.5 minus 2x, and we got everything, we got length, width, and height all in terms of the variable x. Okay? Those 3 steps are the hard part. Okay? Because as soon as we get to the next step, then it's just the stuff we learned in chapter 2. Okay? All right, so step 4 is now find the critical points, which means do the derivative, set it equal to 0, and consider where the derivative is undefined. So if you want to add that to that step. But critical points are those 2 things, where the derivative is 0 and where the derivative is undefined. Okay, so when we say find the critical points of the equation, that's what you're doing. Doing the derivative, setting it equal to 0 and solving, and checking to see if it's ever undefined. Okay, after you do that, identify your endpoints or your end behavior. Now, because it's possible there aren't any inputs, we're going to do that in the next problem. It's possible that there is no smallest input or biggest input. It could go to infinity. Well, then that's where we kind of think about limits, right? One of the reasons that's good, we talked about limits as x goes to infinity. Maybe it's possible that negative infinity are your inputs, which technically aren't even inputs. And so then what you do there is you might not have points to put in your list of candidates. You might just have to discuss what's happening as the inputs get really big. What's happening to the volume, what's happening to the area, what's happening to the profit, or whatever. Okay, what happens to the profit is you make an infinite number of books to sell. You know, well, maybe not. Because the more books you have to sell, maybe you got to hire more people, you got to build a new building, you got to get more machines, you got, maybe your costs go up to the point where your profit actually goes down. Okay, run out of people to sell to. I mean, there's just a lot of those. Okay, so all right, next one, number 6. Use list of candidates, which we did in the 2 examples we've done so far, or a number line. Now, I told you guys a minute ago, no number line, and I'll tell you why you might need a number line on some occasions. List of candidates most of the time. Use list of candidates or a number line or some justification to identify the min and the max. It might be in some rare problems that because of the situation, you could just kind of discuss what's happening to describe the min and the max. Okay? But there has to be some justification. The list of candidates is the most commonly used justification for most of the problems because you have multiple places where the maximum could be. So you compare, biggest one is your max, littlest one's your min. All right, and last but not least, answer the question that is asked using the appropriate units. All right, questions so far? question will come until you get into actually working one of these problems. But anything about the process? All right. Here's the last problem we're going to work on. You're going to have one similar to this in your homework. Okay. So here's the line y equals negative 2x plus 2. So maybe in your notes here you can jot this down, make a quick sketch of it, make it nice and big so you can see it. But just simple little line here, y-intercept of 2, down 2 over 1, down 2 over 1. Okay. So we got that one. Okay. Here's the problem. Find the point on that line that is closest to the origin. Isn't that reasonable? Does it seem like there would be a point on that line? Matter of fact, somebody come up and mark it. There. About where you think it is. All right. Does that seem reasonable? It seems like points out here would be farther away from the origin. Points down here would be farther away. Somewhere right in this vicinity is a point that is closest to the origin. Now, how is that a max or a min? It's a minimum distance, right? Step one, identify what you're trying to maximize or minimize. We're trying to find a distance, a minimum distance. Okay, step two is write an equation for that. Right? So what do we need? We need a distance equation. So what should we call it? Good idea. Way to go. All right. D, and some of you, just to be ornery, will call it P equals or something. But I would call it D equals, right? It's for distance. So we need a distance equation. We're going to be doing D prime here in a minute, right? So we want D equals. So the distance, so I'm going to go ahead and put in that point that Nolan gave us. And we think it's about there. So we think this is the distance we're looking for right here. How do I write that distance? Isn't there a distance formula from algebra class? You got to remember that? Well, yeah. But you could just do Pythagorean theorem too if you wanted to. Right? But the distance between 2 points. Right? Now, what is this? This point is 0, 0. What's this point? Oh, we don't know. So what should we call it? How about xy? Right? Because, and the reason we can use xy, you might say, why not AD? Why not, CD? Well, because this is our equation, right, of that red line. And so y equals negative 2x plus 2 is, all of these points on here are xy points, right? Because they equate, yes.
Can't you find the point that's closest to the origin by just using
Way to go, Sam. Ruin it. Yes. In geometry, you do not need calculus for this problem, actually. You're right. But it's kind of a cool one to use the calculus on because it shows certain things. But you're right. There is a fact from geometry that says the closest distance from a point to a line is, well, it's starts with a P, big long word, perpendicular. The closest distance from a point to a line is the perpendicular distance. So you can get the slope of this line, which is negative 2. So this line would have a slope of positive 1/2, opposite reciprocal. It goes through the origin, right? So this line would be the equation y equals 1/2 x. We can find where those two intersect, and yes, we could find it. That's right. Using that fact, we could do it. So you're right. This wouldn't need calculus. Okay? Matter of fact, we could just do it real quick. So that line is 1/2 x, and where would that equal? Negative 2x plus 2. That is, add 2x over there, that'd be 5/2 x equals 2, so x would equal 4/5. Does that look reasonable that would be about 4/5 for an x coordinate? Looks like it. Okay. So, yes, and that's good. That's good that you brought it, okay? But let's go the calculus route. Definitely longer in this case, the calculus route. But many times they're not that simple that we can do it. All right, so back to this. So we need a distance. So let's call that xy. So what's the distance formula? The distance formula says the square root of, subtract the x's, so x minus 0 squared plus y minus 0 squared. Now all that is Pythagorean theorem. All we're doing is finding this hypotenuse. This distance here would be its x-coordinate minus 0. This distance here would be the y-coordinate minus 0. And then those two lengths squared and then the square root. Pythagorean theorem. Okay, but that's the distance formula. Now the problem is that's got two variables in it. And no, we can't just square root those and call that x plus y. Hopefully you're not even thinking of that. Okay? So we got this distance equation, but it's got two variables, so how could we get rid of one of those variables? Step 3. Use other information or secondary equations to eliminate and get it in terms of one variable. Right there. We can, since y is equal to this, we can take that and substitute it in for that y right there. So d equals square root x squared plus, and in place of y, we can put negative 2x plus 2 all squared. Now that's, I mean, we could FOIL that and do some stuff. We got calculators, fancy, we pay good money for those things. So we're going to use it. Okay, so that's d right there. That's our distance equation. So we're done with step 3, which is get the equation in terms of one variable. Now, as you do more of these problems, you might have thought about doing that right here. Instead of calling this point xy, you might have thought of calling this point x and negative 2x plus 2 right there, right? Because that's what y is. All the points on this line, the y is negative 2x plus 2. So that helps you eliminate a variable right away, but it's still the same thing. You're just doing a substitution. All right, so there we go. So what's the next step? Take the derivative. Okay, John, you on it? All right. So we're going to do the derivative of that. Okay? So we do the derivative of that thing, and it's kind of messy. Now, I'm kind of curious why they gave you a decimal. Oh, you have, okay, scroll up. Yeah, delete that. I don't like that one. I like that one. You thought it might be simpler, right, if you did that? Yeah, just delete that one. Get that out. Okay. Oh, not that one. Can you undo on these things? Is there an undo?
Yeah, Control Z. It's just like.
Oh, just like on a computer. Nice. Control Z. Cool. All right. I like that.
I'm so untech.
I wish I. Good idea. Okay.
I love that word.
I should have known that. Like Control S works. And, yeah. All right. Now, but there's the derivative. Now again, it's kind of messy. That who cares, right? I mean, the calculators take care of it for us. Now you do need to write that on your paper, though. Okay, so you do need to write down. I don't need to because I just don't need to. But you need to. Okay, and then we're going to set that equal to 0. Okay, so write down, even if it's kind of a mess, write down that derivative, and we're going to set it equal to 0, which means we can solve. But I am going to save you a little bit here on your calculators. So before you don't do anything else, John, here, but if everybody else wants to type that in or make sure you know how to. So we do that derivative. Again, you got to make sure you get everything squared that's supposed to be squared. I think you did a good job there. Now, we want to know when the derivative is 0. Now, we have a fraction here, and this happens in the messy ones especially. You get this fractional thing. When is a fraction 0? When the top is 0. So we do not need to solve this whole big messy thing, because sometimes when we do it, it gives us some weird things. All we really need to do is ask, when is the top 0? And that we could probably just do in your head. What is it? It's 4/5, right? Yeah, okay. But it's 4/5, right? And so when the derivative is 0 is when the top is 0, and even if it was a little messier than that, you could do a solve just on the top. I mean, it's not that hard. You just grab it and do a solve, whatever. But you get 4/5. So x equals 4/5 is our solution to when the derivative is 0. So that's one of our candidates, right? Now you might even prefer a decimal on that one. You might even prefer 0.8. Okay? All right, so that's one candidate. Now what's another candidate we got to think about? Where the derivative is undefined. Now this might be because it does have a bottom. So what we care about to see if this is undefined is what? If the bottom is 0, well, we can just solve that. So let's type in, let's do a solve. Go ahead, John. So let's do a solve, and let's set the bottom, well, not the whole thing, just the bottom. Okay, so we're going to, no. Yeah, I think you just got to type this. Solve, solve, solve. Okay, so we're going to take the bottom and set it equal to 0 and solve it. Now, actually, you could do it. You wouldn't even need the square root, right? If the thing in the square root is 0, then square root is 0, 0. But that's fine. Use the square root. So now, man, make sure you go outside the square root, which he did, and then comma x. And what's that mean? It's never undefined. Okay? So d prime is undefined never. Okay, so we've got a candidate there of 0.8, which is when the derivative is 0. The derivative is never undefined. And then we've got to consider what? We've got to consider the endpoints now. What are the endpoints? Well, what are the endpoints supposed to be? They're the littlest and biggest inputs. Right? Inputs. So for this problem, right, what's the littlest x could be? It is negative infinity. Couldn't we have a point out here or out here or out here? And what's happening? Out as x goes littler and littler, as x goes this way, what's happening to our distance? Getting greater and greater. Now, so our endpoints, and these really aren't even endpoints, we can't plug them in, but our endpoints are basically negative infinity to infinity. And when x gets way out here, you're talking about points way out here on the line, then the distance is getting greater and greater and greater. So how many candidates do we have? Well, these really, they're not candidates where I can do a list and plug in, right? I can't really plug in infinity into this, right? I mean, I guess I could. It might not be terrible to do a list of candidates and say d of 0.8 as 1, and then d of infinity. I don't know, I think that AP test graders would not like d of infinity. They might like as x goes to infinity, and you could say it's going to infinity. The distance is getting bigger and bigger. Or you could just write a sentence here that says, okay, the endpoints, as x goes way to the left or way to the right, the distance is getting bigger and bigger and bigger. So the only viable candidate for the minimum is at 0.8, and then find that distance. I think that would be good enough. Okay? But I want to talk about the number line here, because here's where a number line could come in as well. What's the whole purpose of having a list of multiple candidates to check for a max and a min? Well, you don't want to check every number, but when I got 4 different ones to check, like on that earlier problem we did, how do I know which one's a max? Right, and so I just look at the largest one because I have numbers to compare to. If I have 4 candidates there, I can compare them and take the biggest one. What if you only have 1 candidate? Well, but how do you know if it's a max or min? Forget the infinity stuff we just talked about. If you only have 1 candidate, if there are no endpoints, and you only have 1 candidate, how do you know if it's a max or min? You don't have anything to compare to. You see what I mean? You can't do a list of candidates if you only have 1 candidate. Now, we could argue whether the infinities are kind of candidates, and like I said, I think you could make that argument, you could write that out. But you would have to explain yourself and communicate well. All right? But if you have only 1 candidate, here's where a number line can come in. Because if you only have 1 candidate, what that means is, what this graph would be, if I was going to graph the distance, it would really be this kind of thing. The distance is going up to infinity on the left and up to infinity on the right, but in between there's a minimum. Well, if you do a number, so let's do a number line. Let's put 0.8 on the number line. Remember when we did number lines? Because this is worth reviewing anyway. What did we label this number line? Well, what would it be in this one? D prime. Because we plug in now into D prime, right? And so we would take a number on the left here, like 0. We take a number on the right here, like 1, and we plug this into D prime because that would tell us what? Positive or negative, but that tells us that D is increasing or decreasing, right? It would tell us what was going on. But the secret to having only one candidate, and we could go back here, and I want to leave you some time so we won't do it, but we could do the whole vertical bar thing, and we could take our D prime, do the vertical bar, and plug into 0, plug into 1. I'll just tell you what it's going to come out to be. It's going to come out to be negative and positive. What's that tell you? What's the D graph doing? Decreasing then. I don't want to say local minimum because I don't want local minimums here. I want global minimums. This is a local min, but why is it also a global min? Because it's the only one. And I graded AP tests, and here's what they told us to look for. If you have a number line, if you're going to use a number line in a global max min problem, it better be because you only have one candidate. And here's what you say. You look at this number line and you say D is always, and the word always should be in there. Always decreasing before 0.8 and always increasing after 0.8. Therefore, 0.8 is a minimum, a global minimum. Because if it's not always, then you might have a local minimum. If you just say it's decreasing before and increasing after, that doesn't say what it's doing the other times. So there might be other minimums. By saying always, you're saying that is the minimum. That's the key there. Okay? So anyway, 0.8. So what would the last step was, what's the question? So those would be our justifications why it's a minimum. What was the question? The question might have been what point is closest? Well, 0.8 is the x coordinate. How would we get the y coordinate? Right there. For what? Yeah, like, oh, the slug, yeah, the air freshener, you don't plug it, yeah, the air fresheners, that's what it was. Okay, so 0.8, and then what did you put in 0.8, you get like 0.4. So it might be so the question might have been what point is closest to the origin, and that would be the answer, that point. The question might have been how far is it from the origin? What would you do next? How far is it from the origin? You go back to the distance equation, right? Put your 0.8 right in there and get that, right? So it depends what it was asking for, where you would go put that. Okay. Well, here's your homework then, so you can get started here. 4.3, day 1. 4.3, day 1. Now, there's one other thing we've done enough today. You need to start trying some on your own. On number 9, on the homework. Number 4 is just like the one we just did, but they change it to a different point than the origin. So at least you can get started on one that kind of mimics what we just did. But number 9 refers to an example in the book, so you really need to go back and read the example in the book to kind of get a sense of what they're doing there. And it talks about implicit differentiation. There's an alternate method we can go through when we do those derivatives. Right here, when we said get it in terms of one variable, well, remember when we did implicit differentiation, when it had 2 variables, it had x and y in it, and we did the derivative? It is possible to do that. Instead of getting it in terms of one variable, do it with implicit differentiation, but normally that's not a very good way to do it. Okay, so I'll talk about it a little bit tomorrow, and that's what number 9 is about a little bit. Okay, so give that one a try. And then 11 is a little more doable. 17 is pretty hard. Do your best to try to set up as much as you can. So that's the key, is setting these up. And 17 is a hard one to set up. But see how much of 17 you can get set up. I mean, I don't want to right away tell you can't do it, but I'm just telling you. Don't feel bad when it opens. You don't know. Yeah, I mean, I
already know I can't do it.
Yeah, well, I just don't want you to just not do anything. I mean, get the picture drawn. Set up as much as you can. If you can keep going, great. Okay? 22 is much easier than 17. I mean, 22 should be very doable. Okay? Not easy, but it's easier. Definitely easier than 17. Okay, all right. So it doesn't look like much, just like I heard Tim Smith talking about evidently last night's assignment and how, it looked like it wasn't much, but every part had A, B, C, D.
That can be.
I know. Somebody said in the other class, somebody said, yeah, Tim Smith had that on his Facebook and stuff.
I like that. I liked it too. I liked that yesterday.
This one, I think one of them does have an A, B, C, D.